Hello and welcome back to Nunley Math. I am your host, Aaron Nunley. I want to thank you so much for joining me here today. You will notice that we are taking a little bit of a different approach to our video today. Rather than using PowerPoint and just kind of talking our way through that, we're going to do this with more of a paper pencil method, and there's a couple reasons for that. Primarily, this has to do with the amount of time it would take to create a PowerPoint using all the different points and coordinates we're going to need today as we talk about graphs of functions. Plus, I think there's some things that I'm going to need to add in as we go, and it's just going to be easier to handwrite those than it is to try and get them to look good with the PowerPoint. We are talking about how functions look when we graph them, and we're going to be talking for the next several sessions about the different types of functions that exist and that are relevant to us as Algebra 1 students. Now, certainly there are an infinite number of different possible functions we can generate. We like to cluster or group those functions together based on common features. And specifically, through this course, we're going to be looking at 7 specific types of functions. And we're going to be looking at them in great detail. I will tell you that I'm going to try and split this up into a series of short videos, probably 5 to 10 minutes long a piece, if I can, where we spend some time focusing on a specific type of function. And then after we've gone through each individual type of function, we're going to talk about them collectively as a group. You will notice that I've given you a table. In this table, I have given you a relation. This one happens to be a function. I've got it written right here in the center column, and I circled that, but you cannot see it because of the black ink. But know that this is our function. Just like we talked about before, we're going to have a domain. The domain values go into the function, and they put out a range value. And then I'm going to take those and list them as coordinates that I can plot on a coordinate plane. Now, when I do this, hopefully the values that I pick will work. I might pick some values and put them in, and they might not work. But when we're finished, we'll look at the things that did work and then the things that did not work, and we will create a domain and range for the entire function based on that. Now, I am going to go through some of this very quickly because you're watching it on a video, and I don't want to have a lot of downtime or dead time. I would suggest, though, that as I talk about doing things, that you pause the video periodically and you try doing those things on your own before watching me do them on the video. So here we go. I have f of x equals 3x minus 4, and I'm trying to think of an input value that might work. I tend to pick easy numbers to start with. So I'm going to stick a 0 into this function and get 3 times 0 minus 4. Well, f of 0 is 3 times 0 is 0 minus 4 is negative 4, giving me the coordinate 0, negative 4. Remember, the job of the function is to take my domain value and use some rule or pattern to match it to a range value. X is always the first value or the domain. The range is always y or f of x or the second value. And on a coordinate plane, the first or x value goes right and left. So I go over 0, and then I go down 4 to negative 4. If you're having trouble with graphing on a coordinate plane, you probably need to go back and pick that up before trying to continue with this video. Let me try some other points. I can pick anything I want. Let's try a 1. I'm not going to write the f of 1 every time. I'm just going to go ahead and do 3 times 1 minus 4 and get negative 1, which I will graph. I'm going to put in a 2. 3 times 2 minus 4 is 2, which I will then graph. 3 times 3 is 9 minus 4 is 5, and I get 3, 5, which I will graph. If I put in a 4, I get 3 times 4 minus 4, which is 8. And 3 times 5 minus 4 is 11. Notice that my table happens to have 1, 2, 3, 4, 5, 6, 7, 8, 9 rows in it. That is purely arbitrary because it fit nicely on the paper. Just know that sometimes if you look at your graph, after graphing several points, you can see a pattern and you may not need to continue all the way through the end of the graph. There may be times where I have not given enough lines and I tell my students you might have to continue going. I feel pretty satisfied that I know what's happening to the graph over here. It's always a good idea to go ahead and try some negative values as well. This is -7, which is here, and -10, which is here. I always try some negative values because sometimes on the negative side of the coordinate plane some odd or unusual things will happen, but it did not seem to happen here. It did end exactly as I expected it to. Hopefully you can look at this and recognize that these dots all fall into a straight line. Now technically I don't need to say straight line because all lines are straight. If it's not straight, it would not be called a line, it would be called something else. And since all of those values worked and fell into a line, I'm pretty confident that everything along that path will fall into a line. I could try decimal values if I wanted to. So if I wanted to put in 2.5, 2.5 times 3 is 7.5, minus 4 is 3.5. The coordinate 2.5, 3.5 does fall in that line as well. If I wanted to, I could try a very large number like 10. If I put in a 10, I get 26, which is also going to fall along that line a little farther up the way. Now, many of you are probably already familiar with this type of function, the type of function that makes a line. Of course, we call that a linear function. Linear functions can all be written in the form y equals mx plus b. They won't always be written that way, but they can. Certainly, if you've gone through a pre-algebra class, this pattern is probably familiar to you as well. You also probably know that the graphs of linear functions always form a line. Now, there are a couple things I want to point out. First of all, there are faster ways to graph a linear function than what I have shown you here. In fact, this is probably the worst possible way or the least efficient way that you would graph a linear function. I am being intentional about choosing to show it this way because I want to give you a method that you can use on all of our functions. Regardless of what kind of function I give you, you can always plug in your x value, solve to find your y or f of x, and then graph it to see what it looks like. However, that is terribly inefficient. What we want to do is we want to begin to develop skills that allow us to graph these without having to go through point by point by point. Certainly, many of you, knowing that this is a linear function and knowing it's going to be a line, could have come up with a faster way to do it. We would talk about those in our linear equations or linear functions unit, which I choose to teach after I teach functions as a whole. Many teachers will teach linear before they teach functions as a whole, but I like this method a little bit better. If you're interested in my rationale and reasoning behind that, please feel free to leave me a comment in the comment section. I'd be more than happy to share that with you offline. But that's really more of a teacher discussion than a student discussion. Can you think of some patterns that exist in linear functions that might save you some trouble so that you don't have to graph this every single time, or you don't have to create a table that's this long every single time? Here's a thought for you. If I have 1 point, there are an infinite number of lines that I can draw through that point. But if I have 2 points, there's really only one line that can go through those 2 points. You see, if I know ahead of time, just by looking at this, that this is going to be a linear function, I really don't need to draw or plot 10 or 15 points, or in my case, I think I did 8 points in order to do that. In order to get the line, I really only need to put 2 points into my table. Now, in practical terms, I probably should do 3, and if I have a tendency to make calculation errors, I should do 4 to give myself confirmation that those points are not in the wrong or not in the incorrect place. However, you should know that if everything is done right, you really only need 2 points in order to draw this line. Imagine that, being able to look at your function instantly recognize that it's linear and knowing, oh, I don't need to do a table of 8 or 9 values. I only need to do a table of perhaps 2 or 3 values. That can save you a lot of work. And that's really why we're having this discussion about functions, is I would like for us to be able to take all 7 of our major function families, be able to instantly recognize them so that we don't have to do all of this. One other thing I want to mention to you is domain and range. Remember, the domain is what x values you can stick into your function. It's this list of inputs. Notice that every input I chose matched to an output. Notice that that worked for the entire space of the graph, and I was able to see that the pattern seems to continue on and on. Knowing that, I can conjecture or assume that if I were to go out farther and farther along this number line, no matter what x I picked, it's going to work. If I put in a 10, I get 26. If I put in a 100, I get 296. If I put in 1,000, I get 2,996. No matter how big a number I pick, it's always going to match to something. No matter how small a number I pick, it's always going to match to something. Notice the graph continues moving to the left. If I put in negative 1 million, I get negative 3,000,004. Because of that, we say that our domain is all values of x will work as long as those x's are real numbers. Remember, real numbers are just any number that can be found on a number line. All x as long as x is a real number. Now, once I've plugged those domain values into my function, I want to look and see what comes out. I can put anything in I want. I want to know what can come out. Well, let's look at where our graph goes, up and down. Remember, the y values, or f of x values, are along the y-axis. So if I look at this line, and I assume this pattern continues on and on and on forever, notice it keeps going up and up and up. That means no matter what value of x I put in, or no matter what value of x I put in, I can get a number that's a y. And no matter what y I want to find, there's always an x that will give that to me. The same thing happens as I'm going down. I'm going down, 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 down. No matter how low I go, there is an x that will give me the number I want. Because of that, I would say that every value of f of x or every value of y will work as long as that value is along the number line or is a real number. That's our domain, and that is our range. Just as an example, let's say I wanted to get a y value of 50. If my function says y, or f of x, is equal to 3x minus 4, and I want to know what number will give me a 50. Well, I just put a 50 in for my y and solve. 54 equals 3x, divide both sides by 3, x equals, I believe that's an 18. If I would like to get a 50 out of my function, I just need to make sure I put an 18 in. A couple other features I would like to point out for you. This point right here where we cross the y-axis is called the y-intercept. This one happens to be the point 0, negative 4. This point right here where we cross the x-axis is called the x-intercept. I don't know exactly where it crosses because it is a decimal value. I do know the y-coordinate is 0. If I know the y, just like before, I can find the x by putting a 0 into the function. And let me use good math habits. Rewrite, substitute, and solve. Notice x equals 4/3. So this is 1 1/3, comma 0, your x-intercept. Here again, this is not the best or most efficient way to work with a linear function. We will get to that farther down the road. However, it does teach us some very important principles, and that's the reason I'm doing it this way. Over the course of the next several videos, we'll be looking at other types of functions and some patterns that emerge there. Then we're going to come back and put them together and talk about how seeing those patterns can be useful to us. Hopefully you found this helpful. If not, please make sure you let me know what I can improve. If you did find this helpful, please go ahead and give us a like and a comment comment in the comment section. Make sure you like and subscribe, as well as turn on your notifications so that you can follow along with us as we finish this entire Algebra 1 unit. Thank you so much for listening. Best of luck to you. Take care.